Are you struggling to understand how Android handles background tasks? In this Jetpack Compose tutorial, you'll learn how to master background processing in modern Android apps using Kotlin Coroutines WorkManager and StateFlow. Whether you're a college student studying computer science, a beginner Android developer, or a professional brushing up on your skills, this video walks you through real-world examples and best practices for concurrency and background work to help you build responsive, scalable apps. A lecture on Android background processing by the programming professor. Let's begin with an overview of what we'll cover. First, we'll talk about background tasks and why they're necessary. Then we'll explore the difference between main and background threads and move into Kotlin Coroutines, which are essential for concurrency in modern Android development. We'll discuss side effects and how to manage them with launched effect. From there, we'll walk through the Countdown Timer app, demonstrating background processing in action. After that, we'll learn about WorkManager and how it enables scheduled background tasks. Then we'll wrap up with how Android uses notifications and how Kotlin flows and StateFlow help manage asynchronous data streams in the UI. Android applications run most of their code on a single thread called the main thread or UI thread. This thread is responsible for drawing the UI and handling user interactions. The system sends messages to the main thread through a message queue, such as drawing a composable or processing a touch event. If the main thread is blocked, for example, by a long computation, it can't process messages, making the app feel frozen. If the delay is too long, Android shows an application not responding dialog, which can frustrate users and lead to force quits. Let's look at a practical example. The Fibonacci demo composable uses a recursive function to calculate Fibonacci numbers. When the user enters a large number like 40, the computation is so time-intensive that the app freezes temporarily. This happens because the main thread is blocked. Ideally, your app should render at 60 frames per second. But when the main thread is busy, it can't keep up. You'll often see logcat warnings like, "Skipped 59 frames, this visual stuttering is what developers call jank." To avoid blocking the main thread, we delegate time-intensive work to background threads. These are threads that Android keeps in a pool, ready to handle heavier tasks. Instead of freezing the UI, we can hand off expensive operations like file I/O or network access. In Android development, the go-to solution for managing background threads is the Kotlin Coroutine. Coroutines let you write asynchronous code in a sequential style. They can be paused and resumed later, and they don't block threads. This makes them perfect for work like API requests or database transactions. In a composable, you create a coroutine scope using Remember Coroutine Scope, and then launch a coroutine with the launch function. For example, when a button is clicked, a coroutine might wait 2 seconds before updating a message. This non-blocking delay is smooth and efficient. When you want a function to pause without blocking, you use a suspending function. Declared with the suspend keyword, these functions can only be called from coroutines or other suspending functions. For instance, calling delay inside a suspending function lets the system do other work while waiting. It's a lightweight, thread-friendly way to wait for tasks to finish. Coroutines can run on different threads depending on their dispatcher. Dispatchers.main runs on the main thread and is used for light tasks like updating the UI. Dispatchers.default is for CPU-heavy work like complex calculations. Dispatchers.io is best for reading from or writing to a database or network. When launching a coroutine, you can specify which dispatcher it should use. This gives you fine-grained control over performance. Each coroutine launched with launch returns a job. A job is a handle to the coroutine and allows you to control its life cycle. Jobs can be in states like active, completing, completed, canceling, or canceled. You can call cancel on a job to stop it mid-execution. This is essential for cleaning up resources and stopping unnecessary work. In Jetpack Compose, side effects are changes to state that happen after the UI has rendered. A common way to handle this is using launched effect. This composable starts a coroutine when it enters the composition and cancels it when it leaves. For example, you might use launched effect to show a message 2 seconds after the screen appears. It's important not to use this inside callbacks. Use launch for those instead. Launched effect takes keys that control its behavior. If any key changes value, the coroutine restarts. This is useful for animations or operations that depend on changing state. For instance, if you increment a counter that's used as a key, launched effect restarts and runs its block again. It's a powerful pattern for reacting to dynamic UI changes. Let's look at a concrete example using a snack bar. The timer example composable uses a snack bar host to show a message at the bottom of the screen. The visibility is controlled using snack bar host state. If a countdown value is under 10, we increment it every second using launched effect. Once it hits 10, another launched effect shows a snack bar saying the timer has stopped. The Countdown Timer app lets users pick a time using number pickers, then shows the countdown using a circular progress indicator. You can get the starter code from the GitHub repository linked in the slide. The app uses Android View to include number pickers, which aren't yet available in Jetpack Compose. When the app launches, users can choose a time, but the timer won't start until you implement the button logic. To start the timer, you implement the Start Timer method in the View model. This function converts the selected hours, minutes, and seconds into milliseconds. Then, using a coroutine inside View model scope, the countdown starts. Every second, it subtracts time from the remaining milliseconds until it reaches 0. Once finished, it updates the state to indicate the timer is no longer running. The circular progress indicator gives a visual cue of how much time remains. The animated time indicator composable uses animate flow-tas state to smoothly animate the progress from full to empty. This makes the countdown more intuitive for users. By adding it to your timer screen, you enhance the UI with dynamic, user-friendly feedback. To cancel the timer, you implement a cancel timer method in the View model. This method checks if the timer is running, cancels the coroutine, and resets the timer state. You also override the onCleared method so that the timer is automatically stopped when the View model is destroyed. This prevents memory leaks and ensures that your app behaves responsibly. Sometimes your app needs to run tasks even after the user navigates away. That's where WorkManager comes in. You create a worker by extending Coroutine Worker and overriding the doWork method. This runs in a background coroutine and can return success, failure, or retry. It's perfect for long-running background operations. To make our countdown timer app keep running in the background, we add a timer worker class. This worker gets the remaining milliseconds from input data and continues the countdown. It posts notifications to the status bar so users know how much time remains. This is helpful when the app isn't visible, but the user still needs updates. The timer worker keeps posting notifications every second until the timer finishes. Once time runs out, it shows a final message. 2 helper functions handle this. Create Timer Notification Channel sets up a notification category, and Post Timer Notification builds and posts the actual messages. Both are called from inside the worker's coroutine. In the main activity class, we override onStop to check if the timer is running. If it is, we start the worker and pass in the remaining time. We use one-time work request builder to create the work request and then enqueue it. This ensures the countdown continues even if the user leaves the app. Notifications are short messages that appear outside your app's UI. They show up in the status bar, in the notification drawer, or as heads-up alerts. Users can tap a notification to open the app or swipe to dismiss it. Notifications are an essential way to keep users informed about background tasks. To post a notification, you first need to create a notification channel. This is required for Android 8.0 and up. The channel defines things like sound, vibration, and importance. The timer worker code sets up a channel with a name and importance level, registering it with the notification manager. This ensures notifications are properly categorized and displayed to the user. For the countdown timer, we use a channel with low importance to reduce interruptions. Once the channel is registered, we can post notifications through it. To post a notification in Android, use Notification Compat Builder to set properties like icon, title, text, and priority. Check Are Notifications Enabled before calling Notify to display or update the notification by ID. This ensures your notification appears correctly and respects user settings. In the Timer Worker class, we build a notification using Notification Compat Builder. We set the icon, title, content text, and priority. If notifications are enabled, we post the message using Notify. Android Studio might require you to add the post notifications permission. Make sure you do that to avoid crashes on newer Android versions. Android 13 introduced new permissions for posting notifications. You need to add a uses permission tag in the manifest and request the permission at runtime. In the countdown timer example, we use Register for Activity Result to show a permission dialog. If the user accepts, your app can post notifications. If not, the app should gracefully avoid trying to notify. In OnStop, we check again whether permission has been granted before starting the worker. If not, we skip the background notification. This is important because trying to post a notification without permission on Android 13 or later will fail silently or even crash the app. Kotlin flows are a way to stream data from a producer to a consumer asynchronously. You create a flow using the flow builder and use emit to send values. The consumer collects those values with the collect function inside a coroutine. This is useful for anything from loading data to receiving updates over time. A StateFlow holds a single value and emits updates when that value changes. In the view model, you create a mutable StateFlow, then expose it as a read-only StateFlow. Composables can collect it using collect as state with lifecycle. This setup ensures the UI always reflects the current state and reacts to changes smoothly. Let's summarize what we've learned. Background tasks keep your UI responsive and efficient. Kotlin Coroutines help you manage these tasks smoothly, while LaunchEffect and StateFlow keep your composables in sync. WorkManager lets your app do work even when it's closed. And notifications keep users informed. Just don't forget the permission if you're targeting Android 13. All of these tools come together beautifully in the Countdown Timer app, which you can use as a template for more complex background processing features in your apps. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.